I still need to show you how to get factoring from order finding. So first, let me say the second fastest classical algorithm is the quadratic sieve. And so I'm saying most classical algorithms. So suppose you have n equals p times q. Actually, they work in more general cases, but we'll just worry about the case of 2 primes. So the first step, or rather, actually this is really the only step. The trick is to find x squared congruent to y squared mod n, x not congruent to plus or minus y mod n. So suppose you're trying to factor 21. You get 4 squared equals 25. I'm sorry, not 4. 4 equals 4 is congruent to 25 mod 21, right? Because 25 minus 4 is a multiple of 21. No, wait, is this going to work? Yeah, it's going to work. So 4, these are both squares. And now we have 5 minus 2 times 5 plus 2 is congruent to 0 mod 21. And whenever this happens, one of these contains p and the other contains q. Or rather, whenever these are not, whenever neither of these is 0, you have a product of 2 numbers, which is 0 mod 21. And so we know that the product has to contain 3 somewhere, and it has to contain somewhere. And if neither of these factors is 0 mod 21, 3 has to be contained in one factor and 7 in the other. And then what you can do is you can use Euclid's algorithm for GCD to get P and Q. So whenever you get 2 squares which are equal to each other, you're essentially done. And this is how the quadratic sieve works. And that's the second fastest classical factoring algorithm known. And how do we find x squared, y squared? Well, let's look at g, the function f of x equals g to the x mod n. So this is periodic because f g to the r is congruent to 1, then g to the x plus r is congruent to g to the x mod n, because if g to the r plus is congruent to 1, then g to the x plus r congruent to g to the x, because it just multiply both sides of this by g to the x. So that says that f of x is periodic. I mean, it has to start repeating sometime because there are only n possible things here. And whenever it starts repeating, you get a g to the x plus r congruent to g to the x. And that means g to the r is congruent to 1. Good. So that works. So g to the r over 2 squared is congruent to 1 squared if r is even. So let's do an example. Suppose we're trying to factor 21. 1. So 2 to the 0, to the first, 2 squared, etc. So this is 1, 2, 4, 8, 16, 32. 32 minus 21 is 11. So the next element is 11. And 22 minus 21 is 1. 1. So 2 to the 6th is congruent to 1 mod 21. That means 2 cubed is congruent to, or rather 2 cubed minus 1 times 2 cubed plus 1 is congruent to 0 mod 21. And this is 7, and this is 9. And 7 contains the factor 7. 9 contains the factor 3. So the question is, how can this go wrong? And, well, there's a couple of things that could go wrong. We could have started with 4. 4, 16. 16 squared, well, we know 2 to the 6th is congruent to 1 mod 21, so 4 cubed is congruent to 1 mod 21. So we get 4 cubed is congruent to 1 mod 21. 4 to the 3 halves doesn't exist. Well, we can't compute it. So this shows that 4 could go wrong. The other thing that could go wrong is we could do this, and when we look at the middle element, it's minus 1. And that would be a problem because, that would be a problem because then we have x is equal to minus y mod n. And we can't use that. We can't use this trick then. So some things can go wrong, but the great theorem, which is not too hard to prove using number theory, but which is too hard to prove in a single hour-and-a-half session when I have way too much other stuff to cover, is probability of success with what is the sequence? G to the xth is greater than or equal to 1/2 for a random g between 0 for random g less than n. So you choose a random g less than n. You do this repeated squaring, and the probability this will work is at least 1/2. And if it doesn't work, you choose another random g. So eventually, with high probability, you will get a g which lets you factor. Okay. So there's 2 more things I have to do. I have to go back to contingent fractions, and I haven't told you how to compute g to the x.